Hello everybody, and welcome to our video on areas and lengths in polar coordinates. So, let's get started. Recall that the area of a sector of a circle is given by A equals theta over 2 pi times pi r squared. So let's just think about what this means here. So pi r squared is the area of a circle, but the full angle, like a full 360 degrees, is the same thing as 2 pi radians. So the proportion of the sector of the circle is the angle theta divided by 2 pi. So this gives you the portion of the area of the circle that's taken up by that sector. So if we simplify this, cancel pi over pi, and what do we get? We get theta r squared divided by 2. Now, we would like to use this fact to find a formula for a general polar region's area. So consider this polar region here. We've got the angle A and the angle B, and then this curve r equals f of theta. And so this region is the region between theta equals A and theta equals B. And, bounded also by r equals f of theta. So how are we going to construct an area formula? So this construction will be done using Riemann sums, from which we'll derive the appropriate integration formulas, which is how we deal with most area and volume formulas. So we take our region, we divide it up into 3 polar segments, so subintervals of AB. Now, in general, we'll do n segments, but in the image, we're just looking at 3 segments. So you break this up into 3 pieces, which is 4 different points that you've divided your interval on. So 3 subintervals with 4 points along those intervals. And then for each subinterval, we take a sample point. We'll call it theta sub I star. So in the case of this picture down here, what I've done is taken each subinterval, and I've plotted a point in the center of that subinterval. And then using that sample point, the ith region's area is estimated by the area of the sector of a circle. So this looks like a little pi wedge here. So we're modeling the area here as approximately that of each corresponding sector of a circle. So each segment's area is given by r sub I squared delta theta divided by 2, right? That's just the area of a segment of a circle formula up here. But in this case, theta is given by the width of the interval, the delta theta, right? Each of these is delta theta. So then the area of the region is estimated by the Riemann sum from I equals 1 to n of r sub I squared of delta theta divided by 2. That just means you take each segment's area, you add them together, and then you have a total estimate of the area of the bigger region. So if we were to take an appropriate limit where we make the delta theta smaller and smaller, and we take more and more of these little wedges to approximate our area, then naturally you're going to get better and better approximations, and the limit is going to result in the actual area of the original region. So that gives us the following theorem. Given a region bounded by r equals f of theta, theta equals a, and theta equals b, where f is positive and continuous, and b minus a is between 0 and 2 pi, then the area of this region is given by the integral from a to b of f of theta squared over 2 d theta. So keep in mind, our r that we were using in this formula before is really the output of the function f of theta, so we're replacing r with f of theta, so we get f of theta squared over 2 d theta. Now, one other little thing here, this tiny detail, b minus a is in between 0 and 2 pi. That should make sense because if the subintervals covered more than 2 pi, then you would start computing the same area multiple times. So that wouldn't be very helpful. Okay, so let's do an example here. Find the area enclosed by one loop of the 4 leaved rows r equals cosine of 2 theta. So we've talked about this graph before, but let's go ahead and just graph a little bit of it again. So we know that when theta is 0, we get 1. And then we know that when theta is pi over 4, we get 0, and that this graph travels like this. And it does something basically like this for the rest of the time, right? Now, there's a lot of ways we could set this up, intervals we could pick. But one of the things I'm going to point out here is that this each of these leaves, each of these loops, is symmetric over the axis that it's sitting on. So I can actually make things a lot easier for myself by just doubling the area of half of one of these. So if I take this angle here, it's theta equals 0, and theta equals pi over 4. I'll just double the area I get from that, and that'll give me the area of the entire loop. So we should have f of theta squared divided by 2 d theta. So this is 2 times the integral from 0 to pi over 4 of cosine squared of 2 theta over 2 d theta. So then you just cancel out that 2, and that leaves us with the integral from 0 to pi over 4 of cosine squared of 2 theta d theta. So what we have here is a squared cosine function, and if you recall from Calculus 2, in order to deal with something like this, we need to apply the power reduction formula. So in general, the power reduction formula looks like cosine squared of x equals 1 plus cosine of 2x over 2. But it's important to keep in mind here that in this case, we have 2 theta instead of x. So I have to double the 2 theta when I plug it into this formula. So that's going to give us cosine of 4 theta over 2. And if we split this up, that's 1/2 plus cosine of 4 theta over 2 d theta from 0 to pi over 4. So at this point, the integration is pretty straightforward. The integral of 1/2 is just going to be 1/2 theta. The integral of cosine is sine, but keep in mind you would need to do a u substitution here, which I'm going to skip. But the result of that u substitution is going to be that I have to divide this whole thing by 4 here. And now let's plug in. So pi over 4 times 1/2 is going to give me pi over 8 plus sine of 4 times pi over 4. So that's sine of pi, which is 0. Minus 0 plus 0, because sine of 0 again is 0. So this is just pi over 8. All right, well, that's it for example number 1. So let's move on to another example. Now, if you're trying to find the area between two curves, you may have to find intersection points. So sometimes that can be a little bit challenging. We're going to take a look at these two curves, cosine of 3 theta and sine of 3 theta, and try to find their intersection points. So part of the challenge here is that we really need to graph these to see what's going on. If you recall, we know that polar coordinates are not unique in the sense that you can have two different sets of polar coordinates that represent exactly the same points on the graph. So when we set our equations equal to solve for points of intersection, we may not actually find all of them. So it's often important that we graph these things in order to make sure we have a good understanding of where the points of intersection are. But let's go ahead and start with the simple thing, which is setting our equations equal. So cosine of 3 theta equals sine of 3 theta. So we'll find out what r values these are equal for. So whenever their r values are equal, what does that give us? Well, if I divide cosine across here, I get tangent of 3 theta equals 1. And tangent of 3 theta is equal to 1 when the angle, in this case 3 theta, is equal to pi over 4, or any additional pi multiple. So if I divide everything by 3 here, I get theta equals pi over 12 plus pi over 3 times n. So let's go ahead and start graphing these the best that we can and see if we can make some sense of it. So cosine of 3 theta. Well, when theta is 0, cosine is 1, so we start here. So I'm going to do cosine in blue. So we start here. And when do we get our first 0? Well, we get our first 0 when 3 theta is equal to pi over 2. So that's when theta is pi over 6. So let's just get a different color here. So pi over 6. So we get 0 there. And, well, what happens then? Well, cosine becomes -1 when 3 theta, when your input is equal to pi. So that would be theta equals pi over 3. So it's going to be negative radii up to that point, and it's going to extend all the way to -1. So we should end up right about, let's see, I need the mirror image of pi over 3 here. So we should end up right about here. And then by the time we get, let's see, when do we get our next 0? At 3 pi over 2. So divided by 3 theta equals 3 pi over 2. So that's going to be pi over 2 for the angle. So it's going to be here. Then we'll get cosine of 3 theta is 1 when 3 theta is 2 pi. So that's 2/3 of pi. And then by the time we get to pi, we'll be at 3, sorry, not pi. Let's see. 2 pi plus pi over 2. Got to actually think about that for a second. 5 pi over 2 divided by 3. 5 pi over 6. That's when we get back to 0. And then we'll get negative values again. And what you'll see is that after this 5 pi over 6, these negative values lead us back to 0 over here. And now what happens is we repeat this pattern here. So from 0 to pi, we created one pattern of the 3 leaves. So one of the things I want to point out while we've got this opportunity is noticing that when we have 3 theta here, we actually got 3 leaves that just repeat their structure twice within 0 to 2 pi. But when you have that even number here, you actually end up with twice as many leaves. And that's just part of the nature of the geometry of how it lines up. The way these even multiples divide up your 0 to 2 pi interval ends up giving you that ability for each segment to be fully separated. Whereas here, from 0 to 2 pi, we're essentially running across that interval at 3 times the speed. And so we end up, because it's being divided by an odd number, you end up with this weird overlap, where instead of each segment being fully divided, separated from each other, you end up just repeating the same segments twice from 0 to 2 pi. So hopefully that makes some sense. But let's move on to r equals sine of theta, sine of 3 theta, which I'm going to go much faster with. So sine of 3 theta is 0 when theta equals 0. And at pi over 6, it's equal to 1. So what that tells you is that sine ends up going out like this and then coming back here. And then it's going to make another loop like this. It's not perfect, but you can basically see what the idea is. So these graphs are just kind of shifted a little askew from one another, which should make sense because sine and cosine are just horizontal translations of one another. So you get a similar effect here in the polar realm. Okay, so all that is to say, this equation here works perfectly good for the overlap of these things. My picture doesn't necessarily work so good at that. It's a bad picture, but you do see that we get this pi over 12 plus pi over 3 repetition for intersections. But the big thing that's missing here is the pole. So that point isn't included here. So all points of intersection for these curves are going to be at these angles. And it doesn't really matter if you pick sine or cosine to go with. So it's going to be pi over 12 and cosine of 3 pi over 12, which is pi over 4. That's square root of 2 over 2. I actually wrote those in the wrong order. It should be square root of 2 over 2. And pi over 12. Okay, and what else do we got? So pi over 12 plus pi over 3. So pi over 3 is 4 pi over 12. So that's 5 pi over 12. And then for our radius, what do we get? Well, at 5 pi over 12 multiplied by 3, that's 5 pi over 4, which is negative root 2 over 2. And we add another pi over 3. What do we get here? So that's going to be 2 pi over 3, which is 8 pi over 12. So plus pi over 12, that's 9 pi over 12, which is 3 pi over 4. And then we multiply that by 3, so that's 9 pi over 4. So at 9 pi over 4, where do we end up at? It's going to be a positive square root of 2 over 2. Okay, now what happens when we add another multiple there? So, so we get pi over 12 plus pi, which gives us 13 pi over 12. And for 13 pi over 12, Cosine should give us, we multiply by 3, we get 13 pi over 4, which is 3 pi plus a fourth. So we should get a negative square root of 2 over 2 here. Now, what's going to start happening is that if we continue to add more repetitions here, what you see is that we might get different angles, but you'll end up getting the same points in those angles. So, actually this already, let me try that again. This already is a repeating point. That's what I was trying to say. So each of these should only be overlapping at one point here, which is part of the problem when your picture is a little rough. So let's try that again. I'm going to clean up my picture a little to make this a little clearer. Okay, this one should intersect here, and the next one intersects here. And then that one should just intersect on one side. Okay, so let's try that again. So notice here, when we have 13 pi over 12, so that's, you take pi over 12, that's this intersection point. You go another pi, but now your radius is backwards. So your radius goes back to here. So this is the key thing to understand here. We get 3 unique points. We don't need to relist them because this is just a repetition. And all of the points past that are going to be repetitions of those same 3 intersection points. But we also need to include the pole at the center of this. So the pole is our other unique point. Okay, so let's first just keep in mind, as I said before, polar representation of points are not unique. So this pole in particular has infinitely many representations, right? 0, anything with radius 0 is on the pole. And this point is shared by both curves. It's just not shared sort of at the same time, you might say. So they do share the same point, though. They intersect that same point. So setting 2 curves equal doesn't find all of your points of intersection. So that's why it's a good idea to graph them to make sure like something like the pole will be kind of obvious if you graph it. Okay, so for our third example, let's find the area of the region that lies inside the circle. R equals 3 times sine of theta. And outside the cardioid, R equals 1 plus sine of theta. So the circle, R equals 3 sine of theta, is relatively easy to graph. What we should recognize is that when theta is equal to 0, you're going to get 0 for sine. So your radius would be 0. So this is theta equals 0 for the sine graph. And when theta is pi over 2, you should get 3. And the problem's even specified already that this is a circle, which you can show without too much difficulty. But here is the point when theta equals pi over 2. And since this is a circle, that means its center is here. And so its radius is 1.5. So the radius should have this thing going out in either direction like this. Now let's do our best to graph this cardioid, 1 plus sine of theta. So when theta is 0, we get 1. So that puts us here. And when theta is pi over 2, we should get 1 plus 1, which is 2. So it should go up to here. Now, when theta is pi, we should get 0 again. So 1 plus 0 is 1. But pi is facing this way, so it's going to go down to here. Now, once we get to 3 pi over 2, sine is going to go to -1. So the radius is going to go to 0. So this thing is going to curl like this. And then we see that it's going to do basically the same thing out to here. Okay, so what we need to do in order to find this area is find these two intersection points. And then we can imagine dividing up this into segments, yada, 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 integrating by subtracting one region minus the other. Actually, I should specify that says inside the circle and outside the cardioid. So actually, this is the region that we want. Okay, so, well, how do we do that? Well, first we set them equal. 3 times sine of theta equals 1 plus sine of theta. So subtract that, that's 2 sine of theta equals 1. So sine of theta equals 1/2. And that means that theta is going to be equal to pi over 6 or 5 pi over 6. Okay, so theta is pi over 6 or 5 pi over 6. So our integral is going to be the following. The integral from pi over 6 to 5 pi over 6 of our outer function here in blue, 3 sine of theta squared divided by 2, plus the inner function, which is the 1 plus sine of theta squared divided by 2, d theta. So we got to clean this up a little bit. Gives us 9 sine squared of theta over 2 plus 1 plus 2 sine of theta plus sine squared of theta all over 2 d theta. Well, I can pull this 1/2 out in front. And kind of skipping ahead a little, that'll leave us with 9 sine squared plus sine squared. That's 10 sine squared of theta plus 2 sine of theta plus 1. Now for sine squared of theta, we're going to need the power reduction formula for that. And so what do we get here? It's 1/2. The integral from pi over 6 to 5 pi over 6 of 10 times 1 minus cosine of 2 theta divided by 2 plus 2 sine of theta plus 1. Okay, 10 over 2 is 5, so that's when I distribute this, I'm going to get 5 minus 5 cosine of 2 theta. And actually, I'm going to get plus 1 here, so I'm just going to change that 5 to a 6 now. Plus 2 sine of theta. And now we finally got this in a form where we can actually integrate it. So this gives us 1/2 times 6 theta minus 5 sine of 2 theta divided by 2 plus, well, the integral of sine of theta is going to be negative cosine, so we'll make that minus 2 cosine of theta, evaluated from pi over 6 to 5 pi over 6. Okay, so this gives us 6 times 5 pi over 6 minus 5 halves times sine of 10 pi over 6, which is 5 pi over 3, minus 2 cosine of 5 pi over 6, minus the whole thing evaluated at pi over 6. So 6 times pi over 6 is just going to leave us with pi minus 5 halves sine of pi over 3 minus 2 cosine of pi over 6. Okay, so I'm going to try to think a little bit ahead here in my simplification. Sine of 5 pi over 3 is going to give us a negative square root of 3 over 2. So this whole thing will be positive. And that'll be also positive. So that should double. I was hoping that would save me some work and cancel out nicely, but it doesn't look like it will. So we'll just have to use up all the space we've got. So 6 times 5 pi over 6 is 5 pi minus 5 halves times. So again, that's negative root 3 over 2 minus 2 times cosine of 5 pi over 6, which will be negative root 3 over 2. Minus pi minus 5 halves times the square root of 3 over 2. So 5 root 3 over 2. And 2 times 2 is 4. Minus 2 times the square root of 3 over 2. Okay, so let's see what we can do here. Got the 1/2 out in front. 5 pi minus pi is 4 pi. And this is the positive 5 root 3 over 4 and positive 5 root 3 over 4. So that's positive 10 root 3 over 4. And then this is positive square root of 3. And this is another positive square root of 3. So that's plus 2 root 3. If I multiply that 1/2 across, I get 2 pi. And then I get 5 root 3 over 4 plus root 3. So that's 2 pi plus 9 root 3 over 4. And that's just a common denominator. Okay, so the algebra ended up taking a little bit longer on that one than I expected. But there we go. Okay, next we're going to take a look at polar arc length. So let's say we want to find the length of a function r equals f of theta, where theta is between a and b. We first recognize that theta is a parameter with x equals r times cosine of theta. So that's f of theta cosine of theta. And y equals r sine of theta, which is f of theta sine of theta. So as parametric equations, we can apply the parametric identity for arc length. Dx d theta squared plus dy d theta squared, all in the square root, and integrate that from a to b. However, we want this expression to be in terms of r and theta instead. So in order to do that, we'll have to take the derivative of x and y. So, theorem. Given that f prime is continuous, the length of the curve r equals f of theta for a less than theta less than b is given by the integral from a to b of the square root of r squared plus dr d theta squared d theta. Okay, so let's work this out. How do we know that this is true? Well, x is equal to r times cosine of theta, which is f of theta cosine of theta, and y equals r times sine of theta, which is f of theta sine of theta. So if I take dx d theta, I have to apply some product rule here. We get dr d theta cosine of theta minus r sine of theta. And then dy d theta equals dr d theta sine of theta plus r cosine of theta. So all we're doing there is just applying the product rule to these derivatives. Now, if we take these two things and square them and add them, well, what do we get? It's a little bit of a mess, but this first term squared, we multiply the first term by itself, we get dr d theta squared, cosine squared of theta, minus our middle terms being multiplied together, so we get negative 2 times r dr d theta cosine of theta sine of theta, because we get that multiplied twice. And then our last term multiplied by itself is r squared sine squared of theta. And then we do exactly the same thing for this term, and our result is dr d theta squared sine squared of theta minus 2r dr d theta sine of theta cosine of theta plus r squared cosine squared of theta. Whew! All right, let's take a look at this. What can we do here? Well, the first thing we can recognize is that this r squared sine squared of theta and r squared cosine squared of theta, well, sine squared of theta plus cosine squared of theta is 1. So if we factored r squared out of these two terms, we get left with r squared times 1. So that leaves us with this. And we get the same thing here. Oh, there's a little typo in here that I didn't notice. Let me fix that. This one should be positive, because these middle terms are both positive. So when they multiply, we should get a positive. Okay, so now that that's fixed, that makes a lot more sense. So these will both cancel because they're the same. And then here, cosine squared of theta plus sine squared of theta is 1. So when I factor this out of these two terms, that becomes 1, and we get left with dr d theta squared. So that allows us to substitute that back into our parametric formula for length, and that gives us this new polar formula for length. So let's go ahead and apply that to example 4 here. Find the exact length of the polar curve r equals e to the 2 theta for theta between 0 and 2 pi. So we've got r squared plus dr d theta squared, but the derivative of r with respect to theta is just e to the 2 theta times 2. So when I square this first term, I'll get e to the 4 theta. And for the second one, I'll get 4e to the 4 theta. So altogether, that's the square root, that's 5 times e to the 4 theta, I should say, inside the square root. And so I can separate that and pull that product here apart and put the square root of 5 out in front. And the square root of e to the 4 theta is just e to the 2 theta. And when we integrate that, we get e to the 2 theta over 2, and evaluate this from 0 to 2 pi. So this becomes the square root of 5 times e to the 4 theta, or sorry, e to the 4 pi I meant to say, over 2 minus e to the 0 power over 2. This gives us the square root of 5e to the 4 pi over 2 minus the square root of 5 over 2, since e to the 0 power is just 1. Okay, so that's it for example 4, and we're all done here. Thank you for watching.